Non-Spanish speakers here, raise your hand. You have to learn Spanish. No, just kidding. I mean, if you want, it's a very useful language. Thank you for sticking around to my talk. After Wes' keynote, now my job is to bore you to death. And we're going to talk about machine learning for time series forecasting. Let's start with the, required narcissistic slide. My name is Miguel Cabrera. As you might notice by my name and my Sofia Vergara accent, I'm from Colombia. Actually, I studied here in Medellin, in la Universidad Nacional. And then I went to Germany, where I did a couple of masters. And nowadays, I live in Berlin. And I co-organized one of the Python meetups there called PyBerlin. It's the logo that you see down there. I work at New Yorker, which you might recognize because I don't work there. I work here, which you probably don't know because it's a fashion retailer, not a magazine. And so if something similar to it would be like H&M or tennis here in Colombia. That would be like the similar thing. So we say it's a brick and mortar store, and I'm helping them to be like the data science department. So enough of me, let's start. So yeah, in New Yorker, I work in the pricing and forecasting team, and what I want to do with this talk is sort of share with you what I learned in the last couple of years when handling like time series data, in particular in the context of retailing. So there are 3 goals: that you understand the basics of time series first, then that you can identify what are the approaches that you can use to solve the problem of time series forecasting, and then some practical or some techniques that you can use to deal with them. So some things before, so this won't be a code-heavy talk. It will be more like conceptual level, not very detailed, no nitty-gritty, gory details, but rather a lot of concepts. I will assume that you are familiar with the data science stack of Python, namely scikit-learn, NumPy, and whatnot. So, and I will reference them quite often. So, and I will give you, let's say, examples in the sales forecasting, demand forecasting, which is what I do. And in your use case might be a slightly different, but the concept should apply most of the time. As I mentioned, today we're gonna 3 objectives, 3 sections: introduction to time series, machine learning models, and some practical advice. So let's get started. Some basic concepts. So time series and forecasting. So forecasting is about predicting the future as accurately as possible using the information that you have available at the time, including historical data, but also whatever you know about the thing that you want to forecast, the phenomenon that you want to forecast. As I said, most of the time you have historical data, which is normally 2 things. One is a time dimension, meaning you have data that is monthly, weekly, daily based, and then you have sort of a target variable or a feature, or a variable that you want to model and to predict. That's kind of like the basic thing that you have. Then you might want to have different types of horizon, which is short and medium term, which are more operational, something that you can do based on your forecast, you can take action almost immediately, and long-term horizon, which are more like strategic. So to put things into context, in my use case, which is retailing, I'm very interested in demand forecasting. For example, we are a fashion retailer, we have a lot of products with different colors, different sizes, and what we want to do is more or less to complete that table. Just thinking of a pointer. So on the left, you're gonna see it's a table with 2 columns. One is the time dimension, up to the time t is known, and then I, for example, have sales, the number of pieces of a product. And my goal is to complete that table on time t plus 1, t plus 2, up to t plus n. If I complete only up to t plus 1, that is what we call single-step forecasting. If I'm very, I don't know, if I want to complete all the time up to time t plus n, then I will do a multi-step forecast. All right. Now, time series, they have some patterns that you can, some characteristics, some features you might say that you can extract. First is the trend, which is when you see a long-term increase or decrease on the time series. On the bottom left corner, you can see an increasing trend. On the top right corner, you can see a negative trend, a decreasing trend. You also have seasonality, which is times in the time series, in the value of the time series, that are affected by seasonal factors that are basically the day of the year, the time, the month of the year. You also you can also sometimes identify the cycle or cyclic information that is like changes on the time series that are not related to the time. Now, you can use some techniques to take a time series and then extract those characteristics using something called STL. And as you see, on the top is the original time series, and then you can decompose it in the trend and in the seasonal factors. And then you have kind of like the random part, which is the residual. R and Python, you have packages that actually do that. And they are very useful for studying the behavior of the time series. Final thing that I want to mention is stationarity. And I mention it because depending on whether a time series is stationary or not, you can or not use certain methods. Stationarity is a series. You can call it stationary if the properties of the time series do not depend at which time the time series is observed. In other words, if you have increasing trend on a time series, that's already known as stationary, because if you look in the future or ahead in time, the mean or the standard deviation are different. On the top, you can see some examples of non-stationary time series, and on the bottom, like the stereotypical stationary time series. Sometimes you can transform a non-stationary into a stationary time series. And you ask, why are you mentioning this? Well, thing is, in fashion, by definition, we have seasons. In countries where we have actual, like winter and cold, not in Medellin, certain types of fashion products like coats and so on won't be sold as many in summertime as in the winter time, right? And you can see an example here on the left. That's a very seasonal product, and therefore is not a stationary time series. Recap. Now we are experts in time series. We took a look at trend, seasonality, and cycle. We know them. We know stationarity. We know that we can have different horizons, and we know what's the difference between single-step and multi-step forecasts. Okay, so now the boring part hopefully is over. Let's start with the models. But before jumping into them, I want to sort of describe the characteristic that I need in the models I want to use to complete that table. In my use case, I have a lot of non-stationary time series. As you see on the right, there are sample plots of fashion products. So my model, whatever I use, needs to support somehow non-stationary time series. In fashion, in retailer, you generally have many products in different size, colors, or characteristics. And you want to predict or forecast those sales for each one of them. Problem is that some models don't support multiple time series, just one. So you probably want to use a model that you can't, that you don't have to train so many models to, or at least not one per each product. Something that is nice to have is that if you can use information from other products, for example, to forecast the sales on unseen products, new product, or product with not a lot of historicity, then that will be very good. That is called the cold start problem that you might be familiar in the recommender system setup. And for that, I sort of adapted a scorecard, and we're going to take a look at the models, and then we're going to score them based on those characteristics. The idea that when you want to decide which model to use, you can use that scorecard, you can thank me later, and then be happy. If using machine learning or one of these statistical methods, or some people call it AI, there are like three main groups of algorithms that you can use. Either you go into the time series, the traditional time series models that are very old. Back in the 70s, they were invented, let's say. They're very well known, and they're used a lot. You can use ancient machine learning models, like linear regression, support vector machines, and so on. Or the more recent tree-based, well, not like, let's say the most recent is gradient boosted trees. Or if you think you're cool, you might start immediately with a neural net, deep neural networks, recurrent neural networks, and so on. We're going to take a look at some examples of each of those algorithms, really like an overview, so you can get the feeling how they work. And then we're going to get some, like extract the characteristics and when we can use them. Let's start with ARIMA. I know this is, I think this is the only formula I have here, or maybe there's 2 or 3. So the idea with ARIMA is, let's say, simple. Basically, the forecast is based on 2 terms. One is the past values of the time series. So in order to predict time t+1, you use time t. And on the past errors, that's the moving average component, and it's based on the previous errors of the forecast. The integrated part is like the differentiation that you have to do sometimes in order to make the time series stationary. I know this seems very abstract, but I will try to explain with an example. Normally, this is solved using the Box-Jenkins approach, which is an interactive approach when you look at some plots and then you run some tests and whatnot. I'm not going to do that. I'm just going to really quick do it here. So you have the original time series. That's the monthly car sales in Australia, but you can think about like the monthly aguardiente sales in Medellin if you want. Then you do apply some transformation to it. A log transformations, it's very common. Then you differentiate it. You get the integrated part, which is basically remove the trend from the time series. So now it's flat. And with that, if you want, you can plot some correlation and partial autocorrelation. Autocorrelation and partial autocorrelation plots, which allows you to see whether there's seasonal components. In this example, you see there's some correlation here. It's really small in the month 12, meaning there's some sort of like a yearly seasonality in the time series. But I'm lazy, and I'm not going to do this. And what I do, if I have to do that, is I use an algorithm that will do that for me. And ours has something called autoarima. In Python, you can have a package called PDArima. We're going to take a look at that. But if you do that, and you get the algorithm, give you the parameters of the ARIMA. In this case, it's a seasonal ARIMA, which is an extension. And then I can get the predictions and the confidence intervals. This is how it looks, more or less, in code. I import the package, sort of set out the grid search parameters, so to say, and I get the model, which is a stats model kind of thing. I won't say this is optimal. You probably don't want to trust it blindly. You want to maybe take a look at the prediction and so on. Those are the packages that implement them. There's another one called SK-Time, which implements also traditional time series models, but in the more scikit-learn style of transformer, fit transform style. So you might want to check that. I wanted just to mention Prophet, which is a Facebook project that does not ARIMA, but something similar. And I don't have to show you. I don't use it personally, but it's really hot these days. And if you go for traditional time series models, you might want to check it out. So the scorecards. The traditional models are limited in time series when you don't have a clear pattern like you see on the right. And the capability is low. And if you want to use it for, say, things like when you have multiple time series, and I'm talking about thousands of products, then you will have to fit one of those, one of each time series. You will have to fit a model for each one of the time series. And that might not scale very well. Now machine learning, ancient machine learning. So far I've spoken about having the time dimension and having the value I'm interested in. And all the forecasts I made only use those two things. Now, in machine learning, in the machine learning setup, I can use external variables. Let's go back to the aguardiente sales in Medellin. When it's the Feria de las Flores, you're probably going to see a spike on the sales. And you can take that information, put it into a variable, and then use it for prediction. The problem is that, of course, you need to extract those features, do transformations, and then feature engineering becomes very important. Example of feature engineering, you get data from the time series, you calculate some values like mean, average, standard deviation, kurtosis, whatever. Then you, in the case of sales forecasting on fashion, you get product attributes like the category, the brand, the color, and so on. Then you, after extracting them, then you encode those into some sort of like mathematical value, numbers, because machine learning models, they don't understand, categories. And one of the most used one is one-hot encoding. You also can do feature hashing. And if you're a cool kid, you can use neural network embeddings. We're going to take a look at them later. Just an example how the original data might look and how you will end up fitting it to the machine learning model. Because you see that I encoded color, which is a string, into a one-hot encoding type of thing. Need to move fast. I will, so you have different models in machine learning, coming from linear regression and similars, or even using ARIMA and then like using some sort of linear model on top of it. Tree-based models, which were like the kings of the 2010 in Kaggle, particularly gradient boosting, and the ancient supervector regression. And supervector machines, supervector regression. Real quick, I will really talk only very briefly about tree-based models, starting with regression trees. Regression trees are amazing. I love them, but I will love them even more if they worked. They don't. Problem is that they have very low bias, but they have a lot of variance, so they tend to overfit, and they are not very powerful. They are very useful, and you can understand them very well. They basically use a feature, in this case, the X, and they learn sort of like step functions. And with that, they get means on those steps, and that's sort of like they generate the prediction. But because they know they are not powerful, if you have a tree and you put another tree and more trees, then you end up with a random forest, which use a couple of nice tricks like bootstrapping, which is resample the data set, and create a new fake data sets and feed them into new trees, and you can train them in parallel. And they use also subset of the features, so you end up with a lot of trees that have different views of the data set, and that helps you to generalize better. But the actual cool kid in this category is the gradient boosted trees, which in the 2010 in Kaggle, they started winning all the competitions, or most of them, in tabular data at least. And you basically train sequentially trees based on the pseudo residuals, which are a fancy name for the errors of the previous tree. You have some parameters like the learning rate, which is the weight that you give to each of the trees in the prediction. So how much do you trust each of the tree, or that particular tree? And there you have the complexity, like the number of trees, how many estimators you want to have, and the depth, how complex each of those trees is going to be. With Python, you have, most of those libraries are implemented in C++. I think I have I don't know what's saying there. I don't know. Anyways, sorry, I got a bit distracted. So most of those libraries are implemented in C++. The original one was XGBoost. But most of them, if not all, implement a scikit-learn protocol. So you can basically use it straight into your scikit-learn pipeline. In this case, I'm using a research CV on top of LightGBM. Let me see if I can get rid of this. So machine learning, more powerful, but you will have to do feature engineering. That's the thing, and you require expert knowledge. You need to know a lot about it so you can extract those features. And they are, depending on the model you use, they might be interpretable, but not necessarily. The good thing is that if you pick the right model, you can have just one model for all the time series. Now let's jump into neural networks, deep learning, and the things you want to hear. Another approach, some people nowadays, they start with neural nets out of the box. That's the first thing they try, and that's okay. But let's say a more advanced or complex model are also possible. There are 1,000 architectures, so they are just a sample of them. You have the multi-layer perceptron, which is kind of the traditional neural net, and which is drop-in replacement for, say, a linear model, so to say. Then you have the the LSTM and recurrent neural nets that are very good for NLP in other say, problems. The idea was well, if they handle well sequence models in natural language processing, they should be able to handle time series, because you can see that the time series is also a sequence. That is not true all the way, because some characteristic of the time series that you want that they have, the distribution of the target values and whatnot, but some people have made some success. And you also have the sequence-to-sequence transformer and decoder encoder architecture. So as I say, you can use the neural net as a drop-in replacement for a linear model, and in this case, that is a single perceptron, and without the non-linearity, it will be that perceptron will basically be a linear regression. But if you start adding non-linearity and stack them horizontally, then you have a multi-layer perceptron, and if you stack them vertically, then you have a full-fledged neural net. Problem is that you need a lot of data. You also probably need to do feature engineering. And you can see, even using linear models and using other machine learning approaches, they don't they don't work that well with sort of sequence data. It's not natural. See? You don't fit a sequence. You basically transform that into a table, and then you try to send that to the machine learning model, but they don't feel right. It doesn't feel right when you use it. It's just different. So we'll skip this. The idea is that you can use something that the model itself supports a sequence, and that's what recurrent neural networks do, and LSTM do as well. The difference is that you have a hidden context that is also shared across all the steps in the computation. So you computing, for example, t plus 1, the value for t plus 1, you use the previous hidden state. There's a model that I wanted to mention that I sort of like discovered it, and I want to share. It's this deep AR. This is for Amazon. And it's similar to an LSTM with the difference that you can not only use the hidden context, or the context, they call it H, but you also use the output of the neural net as an input. So it becomes, you have the previous state, the current features, and the last observed value, which is autoregressive, which is similar to what we saw at the beginning with ARIMA. So it's pretty cool when you can mix both architecture, and they use it in Amazon for doing like sales and forecasting and demand forecasting, and they look interesting. If you're working in that area in retailing, you probably want to check it out. Regarding tooling, I know there's some TensorFlow fans here, which you can implement any model that you want using one of those. For the multi-layer perceptron, FastAI already have a lot of support for tabular data. So FastAI is kind of like I would call it like a library that gives you a lot of functions to work with on top of PyTorch. And it's very cool, and it has a machine learning course also attached, so it's very nice. And Scorch is a library that is maintained by a colleague of mine that allows you to integrate PyTorch into scikit-learn's pipelines. And if you want to give your money to Amazon, you can use MXNet and Gluon and Amazon SageMaker, and that comes already with a bunch of models that you can use, but you will have to use it, pay Amazon. Though Gluon is a library similar to Keras for MXNet, you can use it on your own machines and whatnot. And there's a library called Gluon TS, which already brings some of the models. So if you want to check it out, this deep AR, you can use it right out of the box. So neural nets, very powerful. They're cool. If you use them, you can tell your friend you use deep learning. You still need some feature engineering. In the literature, I was reading for preparing this talk, there's not like a clear consensus which model works the best. Some people say, yeah, LSTM with this formulation, and other people say convolutional neural net, wave net, and so on. So it's not so well defined. So you will have to try a bunch of them and decide. If you start with neural net, I will advise you to start with a baseline based on multi-layer perceptron, like a vanilla, de toda la vida neural net. So, sort of a short recap. Traditional time series models, they're Asian, but they still work. Actually, there was a competition called M4, and they have a bunch of time series, and the competition was about getting the best prediction for all of them, different weekly, monthly, and so on. In traditional models, a very complex pipeline of traditional models, where they scored the second place. And the first place was a neural net with a exponential smoothing kind of thing inside. So, they're still there. I prefer machine learning, like the gradient boosted. That's what I use currently. We're exploring neural nets, and I will start with the machine learning approach for like traditional machine learning. It's easy to implement. You don't need GPUs or anything. But I think the future is neural nets, and people are moving towards using neural nets, but we are not in, say, how it's called, the ImageNet moment. We are not there yet, or the NLP moment, transfer learning, whatnot. We're still, like, it's an open research area. I have only like 5 minutes left or so, so I will skim some of this. So we already know what are time series, we already know how to use machine learning, but how do you evaluate that your model is doing what you want? There are a bunch of metrics and formulas. And the idea here is I have just two main opinions here. Use whatever you think it makes sense for your problem, looking at the different characteristics of the metrics, but also get one that you can show to your stakeholder. So if you go into your, say, your boss and it's not technical, and you say, no, my MSLE is whatever, they were like, what? They cannot interpret that in the logarithmic scale. So you probably are better off showing them the mean absolute error or showing them how much money you are making from your forecast. Or, well, not them, but the company. I mean, not you. Anyways, most of the time you want to do some sort of variable transformation. So the traditional box cost transformation sort of tries to move the target variable into something normal, because some traditional methods require that the distribution of the target variable is sort of normal-like style. I use the logarithm because it sort of squashes some variances that the data might have. And you can also want to scale or normalize the data so that if you have time series in different scales, you might want to squash them. But be aware that might also have negative effects, and that might also hurt your predictions if your model doesn't extrapolate, like a tree-based model. They cannot extrapolate. They just learn step functions. Now, my advice here, whatever transformation you do, use cross-validation and find it the right one using evaluating in different, say, folds. Coming to that, what I said, because you do that a lot, very commonly, scikit-learn already brings something for you. It's called the target variable transformer regressor, where you send your basic estimator, and then you can pass a couple of functions or a transformer, one to transform the target variables before fitting, and then when you're at prediction time, the reverse transform. So that's so common that you already have the machinery in place. Final is cross-validation. You cannot use the traditional cross-validation that, random splits and whatnot. You have to take care of the time constraint. Because if you don't, you might do something that is really, really bad, that people call leaking data. So you might take data from the future and put it into your model, and then your model is going to perform very well, but that's a lie. It's not true. For example, if I say I scale a feature, whatever, and I scale it using the maximum and minimum, and I calculate that using the, is this a pointer? Trying to, using the whole data. The maximum can be on the white area, for example. And then I'm using information that I haven't seen at prediction time to transform the variables. So most of the time you want to have like an expanding window approach when the trained data is always in the past of the test sets, the data. Sometimes you want like a sliding window approach, because sometimes having more data doesn't necessarily mean a better performance. And have 30 seconds left. There's a bunch of useful predictors like the age, or they call it trend or sequence. I found that it helps. I don't have a paper to cite, but that's my experience. You definitely want to add into your feature some sort of seasonal component, like the time of the day or the day of the week. And you probably want to add something that they call intervention variables, that they are true during a period of time. Going back to La Feria de las Flores, that I really like, you want to mark that in your data set. Okay, during August, I think, there's a fair in Medellin, and that probably affects the aguardiente consumption here. I think so. I don't know. I haven't been. And that's it. Summary. I know time series is not sound or NLP, but when you go to the industry, a lot of the problems that you're going to face is with tabular data, and most of them also that you can model them as time series. And you might get some value for traditional models, depending on your requirements, but I think machine learning and later moving into neural nets might be the way to go. Still, deep learning is not there yet, and you might be good at, like, okay by using easy to train models like even normal linear regression or some tree-based method, and just don't avoid data leakage. That's something that happens quite often, and you don't. Sometimes you have your model there, and you only realize when it's too late and the model is in production. It's not good. Anyways, I will publish the slides with some references and some code there, some image credits that I use, and gracias. Thank you for your attention.